Hello, in this video we're going to work through section 2.3, problem number 23, and this problem asks us to find the formula of the derivative of the function using the difference quotient. Okay, so in other words, we're going to use the limit definition of the derivative function. Now, one thing you should have noticed from section 2.3 is that it looked very familiar to what we did in section 2.2. The difference being in section 2.2, we were actually looking for the derivative just at a single point, just at a single x value. Whereas now we're actually finding the function of the derivative for all x values. And so to use the limit definition for that, we're saying the derivative of the function is equal to the limit as h approaches 0 of m at x plus h minus m at x all over h. So like last time, the first step is to replace the function notation with the actual function itself. So this gives us the limit as h approaches 0. M at x plus h is equal to 1 over x plus h plus 1. And then subtract from that m at x, which is 1 over x plus 1, all over h. Okay, now I need to combine those two fractions in the numerator, and to do so I will need common denominators. So the first thing I'm going to do to these fractions in the numerator is find a common denominator. And the way I do that is multiply the numerator and the denominator of this first fraction by x plus 1. Then I'll multiply the numerator and denominator of the next fraction by x plus h plus 1. And now that I have common denominators, I can combine those two fractions. So I end up with the limit as h approaches 0 of x plus 1 all over x plus h plus 1 minus x plus h plus 1. Oops, sorry, missed something here in my denominator, didn't I? This is not just x plus h plus 1, but x plus 1 times x plus h plus 1. And then over here I have that same denominator, x plus 1 times x plus h plus 1. And I'm not going to multiply those two terms in the denominator together, and just going to leave them separated like that for now, and you'll see why in a minute. But that's just the numerator of what I'm taking the limit of. I have all of that over h. All right, let's see what I can clean up here now algebraically. When I do the subtraction, I have this term here, x plus 1, and I'm subtracting from that x plus h plus 1. So the x minus x would give me 0. The 1 minus this 1 would give me 0. So what I'm left with is this minus h. So let me get my black pen back. So in other words, I now have the limit as h approaches 0 of, in my numerator, the numerator of my numerator, I have negative h because I have 0 minus, let me get this little pointer pen out. I have here essentially 0 minus h, so that is negative h, all over x plus 1 times x plus h plus 1, all of that divided by h. Now I'm going to use the fact that division in fractions is the same thing as multiplying by the reciprocal. So I'm going to say the limit as h over 0 is equal to, this all is equal to the limit of, as h approaches 0, of negative h over x plus 1 times x plus h plus 1 multiplied by, so instead of dividing by h, I'm going to multiply by the reciprocal of h, which is that. Okay, again, a little algebraic cleanup here. I have this h and this h. So h divided by h is just 1. So I can come back, and the derivative of the function is the limit as h approaches 0 of -1 over x plus 1 times x plus h plus 1. Okay, so now I'm all cleaned up here, about as simplified as this can be. So it's now time for me to take that limit as h approaches 0. So in other words, I'm going to look and see what happens to this expression as this value here, this h value here, I don't know if you can see that or not, as this h value here gets smaller and smaller and smaller. Well, as that h value gets smaller and smaller and smaller, this whole term becomes simply x plus 1. And so when I take the limit as h approaches 0, I end up with -1 over x plus 1 times x plus 1, which now tells me that the derivative of the function m at x is equal to -1 over x plus 1 quantity squared. And that's true for all x values.